Hello, I'm Jiefu. I'm currently a student intern at COSP Jiefu. I'm going to be a master's student in language technology at CMU this coming fall. And I'm going to present our paper, InFillmore, Frame-Guided Language Generation with Bidirectional Context. And I'm happy to be with all my great collaborators, Nathaniel, Anton, Felix, and our advisor, Professor Ben van Durme. The key motivations of our work comes from some observations that the state-of-the-art text infilling models are very good at producing human-like text and have been proposed as core components of automatic and interactive story generation. However, there are many occasions where we would like to employ some textual or semantic control over the output, but these infilling models have not yet been equipped with such a mechanism to explicitly control for underlying semantic content. We therefore propose a way for humans or some content planning models to specify discrete semantic content while conditioning on surrounding textual context. To provide semantic guidance, we used more than 1,000 frames defining FrameNet as a signal that constrains or conditions the infilling model. A semantic frame comes from FrameNet, for example, the frame research in this page, including frame IDs, definitions, core frame elements, and the triggering words, also known as lexical units. Why would someone want this resource? Well, having a model that can make inferences on account of both discrete structured semantic content as well as textual evidence allows for a diverse array of use cases, many of which are particularly salient to NLP. For example, as we show in this figure, the model can be used for collaborative story generation with iterative refinement. The model can also be used end-to-end to generate a story all at once, conditioned on a story plan consists of a sequence of sets of one or more frame labels. And it can also be used for semantically diverse generation by asking it to first predict a set of frame IDs that might occur before or after an input, and then generate a sentence for each of the predicted frames. And finally, it can be used to rewrite a given text document in the presence of new evidence. To perform well on this diverse array of tasks, we propose frame-guided generation framework, or generating text conditioned on frame semantic content. This framework consists of two approaches. The first approach is to leverage the FrameNet mapping of frame IDs to a set of associated lexical units, or LUs, which are words that trigger the frame when they are used in a sentence. We use this LU set as constraints for a lexically constrained decoding algorithm, or LCD, that forces the model outputs to contain a frame triggering word for each of one or more desired frame IDs. The second approach imposes soft constraints by fine-tuning a neural LM to condition on the control codes. We built on the recent method called infilling language model, or ILM, that trains a forward generation GPT-2 model for bidirectional context infilling. The first method, called LCD, is a modification to beam search that forces the inclusion of pre-specified words and phrases in the output. It has been widely applied in various areas, such as machine translation, paraphrasing, causal generation, etc. The two main components of LCD are to record the progress through each of those constraints, the bookkeeping phase, and the constraint-aware beam ranking, the beam allocation phase. Our LCD methods follows previous work to use the dynamic beam allocation in beam ranking, meanwhile extend the bookkeeping methods to adapt to the frame guiding purpose. Previous work has explored different ways of constrained bookkeeping, mostly based on the tree representation of keywords or phrases. To enable different type of constraints, for example, namely complete, single disjunctive, etc. in the slides, to satisfy the requirements of frame triggering words, the LU inclusion, especially when there are multiple frames provided, we extend previous work to develop the list of trees representation. Given a list of frame input, for example, the coming to believe and cause harm in our figure, we construct a tree of LUs with morphological variants for each of the frames based on the bipair encoding. We then impose disjunctive constraints with respect to each tree. That is, once the LU is realized, the whole tree will be finished and the progress is advanced. We compare the lexically constrained decoding approach to a second method for frame-guided generation, where rather than modifying the decoding phase of the language model pipeline, we modify the training. We use an increasingly popular technique called control codes, which are special vocabulary tokens that can be used as prefix to generation in order to specify something about the output text. For example, One can train a multilingual machine translation model where the target language to translate into is specified using a special language identification token as shown here. This technique has been used as well for other forms of style and content specification, as well as diverse semantic generation, and increasingly many more. We apply the control codes idea to frame-guided generation by introducing a new special token to the vocabulary for every frame in FrameNet for a total of more than 1,000. We inject them into the vocabulary of the infilling language model, which is a recent forward generation model that conditions on bidirectional context. That is, text that is potentially before or after the generated text. They accomplished this by rewriting the text using special tokens and content reordering so that a forward language model can condition on the provided text and generate one or multiple text infills at the locations specified by blank special tokens. We augment this approach by specifying special frame ID control codes at the start of each infill. We fine-tune the infill language model to condition on one or multiple such special tokens, allowing a high level of flexibility in content specification.
To test both proposed methods, we evaluate them on the story close task using the ROCStories dataset. In this setting, we are given a short 5-sentence story with one sentence masked out, and the goal is to predict that missing sentence. We are comparing two proposed methods, the frame-filling approach, or FFL for short, as well as ILM with lexically constrained decoding approach, or ILM plus LCD for short. Both methods are conditioned on the FrameNet frame IDs extracted from the goal missing sentence. We then test both methods on 3 levels of supervision, single and multiple frames, where frames are randomly selected from the goal extracted frames, and all frame settings. We compare these results with ILM, which serves as a baseline model. In the first experiment, we test how well these models can recover the underlying frame ID sequence of the goal missing sentence. We hypothesize that the goal frame ID sequence contains the underlying semantic content, and we use a state-of-the-art semantic parser to extract frames from model-generated sentences, and we compare them to the goal frames using the recall measure. We see that both FFL and LCD are substantially better at capturing the underlying semantic content compared to the unconstrained ILM model. In the second and third experiments, we asked Mechanical Turk workers to look at the complete 5-sentence stories infilled by different models and identify which sentence out of 5 was model generated. We look at 2 measures, namely the confusion rate and average rank as a proxy for the quality of text generation. Confusion rate measures how often humans fail to distinguish model-generated and human-generated sentences. In the average rank experiments, the Mechanical Turk workers can see all the model-generated sentences for each story, and we ask them to rank the sentences best to worst. In both experiments, we observe similar trends. The first one is that the frame-filling models under multiple frame and all frame guidance are competitive with ILM in terms of generation quality, which means that its ability to produce semantically guided text comes at little to no loss in fluency. At the same time, we observe that frame filling and lexically constrained decoding follow the opposite trends in terms of generation quality, where more conditioning helps the former but hurts the latter. This could be explained by the fact that LCD approach is required to satisfy all the semantic constraints, while the frame filling approach incorporates those constraints in a soft manner and may choose to disregard some of them. Finally, we show how the proposed frame filling model could be used for interactive story generation using a demo app that we developed. First, you can start writing a sentence and ask the model to predict the next one. You can keep adding new sentences or editing the existing ones. Afterwards, you can infill sentence at any part in the story, and the model will suggest you the frames and sentence candidates to infill that sentence. You can keep writing the story all the way through until you're satisfied with the result. In summary, our paper introduces the frame-guided generation framework that uses FrameNet frames to guide semantic content in an infilling model. We propose 2 extensions to an infilling model that efficiently utilize frame semantic information in the form of frame IDs during text generation. Finally, experiments on the story close task show that both our extensions enable high semantic frame fidelity with competitive generation quality. Thank you so much for listening, and we look forward to seeing you in our lightning talk.